So yeah, welcome everyone. This is NOC24 W139 Microelectronics Devices to Circuits. Am I audible by the way? Can anyone confirm?
Yeah, you're audible.
Okay. So let's wait for 5 more minutes to see if other people joins. Meanwhile, let's have a quick introduction of you guys. That please tell me which college you are from and what year you are in, UG, PG. Okay, it will help me to analyze that how far I can discuss the things so that things may not skip over your head. Okay, so you can unmute one by one and just introduce yourselves. Meanwhile, while we wait for 5 more minutes for other people to join, anyone wish to volunteer?
Yeah. Hi, sir, and hi, everybody. A very good afternoon.
Yeah, so which year you are from and which college?
Yeah, my name is Gautami, and right now I'm in the first year of MTech. I
Okay,
recently joined in IIT Hyderabad.
okay, first year PG, VLSI.
Yeah, no, communication signal processing.
Okay, communications, good. Then let's move to the next person. Okay, we are having some responses over the chat. So, third year electronics communication, I assume that it is UG. Anyone else?
Good afternoon. Good afternoon, sir.
Yeah, good
Myself,
afternoon.
Sri Sharma. I'm from NIT-K Solancal, third year electrical and electronics engineering.
Okay, good, good. Anyone else? We have still 3 more minutes before we start. BTech EC third years. Okay, so most of you are third year and above. Anyone else? Let me put it in this way. Anyone else who are in first year or second year of UG? I guess no. So, okay, then you must be familiar with the concepts like band diagrams and all. Anyone? Let me repeat myself that you familiar with the band diagrams and the device operation basic principles, because you see that we can go deep into those stuffs also, but the way this course is designed is to give you an overview of the device physics and then directly move on to the circuital applications. Okay, so yeah, I think everyone is familiar with that. Okay, we'll see. Then another thing I wanted to ask you guys that how do you want this session to go? Because the purpose of these sessions are, that you are given certain assignments if you have enrolled for this course. Then if you have any difficulty to solve those assignments, so those parts we can discuss via the question and answers I will prepare for the week. You can ask any doubt regarding that how this thing is working, or I am not getting this stuff, because I know that in undergrad there are so many concepts which may seem trivial, but you never get a grasp of the key essence, right? So I wish to make it an interactive session. So if you guys are okay with that, so we'll have certain discussions. Just treat me as a fellow student of your classroom only. Okay, we'll just have a discussion and we'll come to a conclusion. There will be cases when I may not be able to answer your questions, but that's fine. Same for you guys also. So we are on the same page in that regard. So, but let us not stop those things to ask questions, okay, to each other. Okay, so again, good afternoon, everyone. Welcome to this course. So the idea is that you guys join every week. It will be better if you join within 3 to 3:05 because I will start mainly after 5 minutes only. So this is microelectronics devices to circuits, and the course instructor, as you guys already know, that this is Professor Sudev Dasgupta from IIT Roorkee. So I am Debashish Nandi from IIT Kanpur. I am assigned as a TA or tutor for this course. So this is a 12 weeks course, as you know, and we go live for the discussion sessions for 3 to 5 every Sunday. Okay. There may be 1 or 2 week, there will be exceptions, but that you will get notified earlier. So these are some key prerequisites which I want you to follow. That please, as you guys already are in third year, so maybe preparing for the placements and MTechs for better understanding or grasping the concepts. So I think you guys all are sincere students. So please go through the lectures beforehand. It will help you to grasp the discussion or be indulged into the discussions what we will be doing in these 2 hours. And then also it is suggested that you have attempted the assignments posted for the last week at least yourself once. Okay. If may have certain doubts, you may not get convincingly, you may not, you might not complete the assignment. That is fine, but at least you should attempt once. Okay. And also some decorum that will keep our microphones muted. And if you have any questions, there is an option of raise hand in the chat box, and also after each questions I'll ask you that if you have any doubt, so we can discuss in that way. And also if time permits, though I have from my past experience that it is I am not able to complete the entire session within 2 hours, but if we have time, we will give a 10 minutes slot to ask your general queries regarding the session. And it is suggested that if you go along with the assignments, what I am doing, or the questions, what I am solving by yourselves in a pen and paper, it will be best. So keep a scientific calculator handy. Okay. And this session is being recorded for information, and it will be posted on a YouTube channel, and those links will be shared to you by the NPTEL team. Okay, so this is week 1. Let's start. So these are certain warm-up questions what I have prepared, and I think these questions are also posted as week 0 assignments to you, right? So let us discuss. So first question is that there is a statement given, right? BJT is a four-terminal device. Is the statement true or false? So anyone wish to answer? Why false, Divya? Yeah, right. It is three terminal. Okay. So just take a moment to understand what BJT stands for, right? It is a bipolar junction transistor. So can anyone tell me what do these three terms mean individually? Why bipolar, why junction, and why transistor?
Bipolar is because the current due to both electrons and holes.
Okay, so by the way, why do we have two kinds of carriers? In metals, we have only electrons, right, which carry the current.
Yeah, because we have two charge carriers, holes and
Why?
electrons. Because it is a semiconductor device,
So why
whereas
do semiconductors have holes?
semiconductors have holes because when they break the covalent bond,
Mm-hmm.
there is a free electron which comes out of the bond, leaving a vacant space.
Okay.
Those vacant space, we are calling them as holes.
Okay. So how does that help in conduction? That is a in the bond, right?
Yeah. So there is hole. There is a vacant place. So
Right.
there are some other electrons which come out of the bond from other covalent bond. those electrons will come into this hole, and that electron which came out of from other bond leave a hole. So like this one electron jump from the hole, and it will be occupied by the electron creating a hole. So this will make a flow of current.
Okay, so you mean to say that holes are absence of electrons, and from bond to bond there will be electron movement from one place to the that vacancy, and then it will move eventually. So it is hole is just a concept, right? It's an
Yeah,
absence
yeah,
of
yeah.
electron. Ultimately, it is electrons who are moving. So there is one thing called free electrons which are in abundance, and they in abundance apart from the bonded electrons or the covalent bonds, and another one is your bonded electrons. So those bonded electrons also takes into conduction in semiconductors, because to move from one covalent bond to that vacancy takes lesser energy rather than freeing up a second electron. You see, so it is all about what least energy path the carriers take actually, right? So you are absolutely right. So basically, we have two kinds of carriers in semiconductors: electrons and holes. So that's why we have, and in BJTs, bipolar junction transistors, both types of carrier takes part into conduction. Can you name another device where the device is kind of bipolar in nature apart from BJT?
FETs, MOSFET.
No, MOSFET is unipolar device. There we will come
Okay,
back
so
to that,
we
right?
are asking about bipolar PN junction.
Yeah, PN junctions, right? In PN junctions also you have the currents in a PN junction are due to both holes and electrons. There is a famous, or I would say infamous statement that minority carrier basically dictates the current conduction in PN junctions, right? But if you plot the current profile, you will see that majority carrier current magnitude is much higher than minority carrier. But the profile is dictated by the minority carrier. So PN junctions, BJT, these things, there are two types of carriers who take part in the conduction. Okay, someone else tell me why it is called junction. Why this term is there, junction. Anyone else? Just try. It's a discussion session, right? By the way, am I audible? It is true if we consider terminal or substrate. Uh, can you explain the question? It's the mid area between two substrate. See, guys, it is better if you speak out, right? Unmute yourself and speak out. You can convey the message much clearer way. So, is it true? It is true if we consider terminal or substrate. So, what substrate you are talking about? Srinivasan V triple E. Is still there in the call? Yeah, can you unmute and please tell me what is the doubt? No, no, we are talking about BJT, right? So what is the body here? It is a BJT. We are not talking about MOSFETs. The question is that BJT is a four-terminal device or not? Can you unmute and ask what is your doubt? Okay, if you are not comfortable, let's move on. Another question is that It's the mid area between two substrates where holes and electrons are transferred from one side to other. No, not really. Okay, anyway, so the junction term comes from the fact that if you see a BJT, the structure will be something like this, right? Though this is not exactly how the device looks like in reality, but if you just take a cut section in the middle and flip it over horizontally, you will see that if you have, let's say, a PNP kind of transistor, this is your emitter, this is your base, this is your collector. So you have these two junctions, right? Two PN junctions. Junctions can be of many type. Metal semiconductor also can form a junction, which eventually forms at these places. So the current transport in a BJT is primarily governed by the properties on these two junctions, these two PN junctions. That is why it was termed as bipolar junction. So governed by PN junction theory. So the last part is what is a transistor? This will be interesting. So this is for anyone. What is a transistor? Guys, I request you to please don't put it in a chat box. You can unmute and speak out. It will be better for you guys only. Once you start to discuss or interact, no, your the potential barrier or the communication barrier will start to reduce, and it will benefit yourselves only in a later, and your confidence will also get boosted up. So it is suggested, please unmute and speak out.
So a transistor is kind of a switch.
No, no. My question was that, yeah, you are right that transistor can be used as a switch. My question is that what is this transistor? Means how does mean you see that why we are taking at this bipolar? Bipolar means two poles. That's how the term come into picture. So what is transistor? How does this term come into picture?
So it's a three-legged device.
So there is no the three-legged device is generally called triodes, right? Tri-electrodes, triodes, not transistors. But what is transistor? Just a guess from the word. What do you think? There are two parts, right? One is trans, one is ester. That means it is basically nothing but your transfer resistor. What do they mean by transfer resistor is that you have one terminal where you have the control, you have other terminal where you have the controlled, right? Means by controlling terminal A or port A, you are controlling the characteristics of terminal B. Okay. So why transfer of resistance? Let's take a black box and consider it has two ports. Okay. So black box is something where we are not concerned about what is there inside. Okay. It's just a box. So let's say you have a input current I, and this input current is flowing out, same current is flowing out. Okay. And let's say if you have a input voltage here V in, and here is a output voltage V out, and let's also assume that there is a gain involved, some sort of gain involved. So let's say your voltage gain is V out by V in. So can you guys tell me that what is the ratio of Thevenin resistances looking in and out? That means your R in and R out. This is basically your V out is what? I out into I, and this is your R in. This will be a minus, there will be a minus sign from the passive sign convention, and your R in into I, assuming that the same current is flowing in the device throughout the device. So you have a basically an amplification of the resistance, right? So the resistance may go up or go down depending upon what kind of amplification you are getting, current amplification or voltage amplification. Okay. So the basic idea is that any transistor action or amplifier action, you can break it down to the fact that the impedance, real part of the impedance or the resistance is changing. That means it is getting transferred, increasing or decreasing. Okay. So from this concept, this transistor word came into being. Now, can you tell me that in a BJT, how does this work? You see that if we consider the emitter base junction, what is the most convenient operating mode of a BJT? Forward active, right? Where what is the conditions imposed on the junctions? The emitter bias junction is forward biased, so this will be your forward biased, and these two junctions is your reverse biased. So in a PN junction, what is the state of the resistances in a forward bias or in a reverse bias? So in a forward bias, do you think the resistance is smaller or higher for a PN junction?
Smaller.
In a forward bias, because you have a high amount of current for a small voltage, your resistance will obviously be smaller, right? So you have a smaller resistance here, and in a reverse bias, just the opposite thing happens. It is kind of a switch, as he has rightly pointed out, that the switch is cut off in the reverse bias. There is a very small saturation current, reverse saturation current is flowing. That means you have a very high resistance. Whatever you are giving in the input swing, there is nothing coming out of at the output. Okay. So this is a very high resistance. So this transition from a smaller resistance in the input terminal to a higher resistance at the output terminal, this action is called the transistor action. Okay. So this is how the transistor term came into being. So this is why it is called bipolar junction transistor. So is it okay? Okay. So just tell me one thing. Do you guys know who invented the transistor first? Shockley, one answer came. So in which year? Basically what,
1948.
right, at 1948 William Shockley invented the BJT, right? The thing which we will study today, bipolar junction transistor. But just a 6 months or 1.5 year back, three people led by a team of Shockley invented the similar stuff. They called it as a point contact transistor. So 1947 was the first physical demonstration of the transistor, solid state transistor came into being. Okay. So this was done by Brattain, Bardeen, and the team was led by Shockley. So if you see your 1955 Nobel Prize, so it was divided equally between these three gentlemen. So this was not your current bipolar transistor, but it was your point contact transistor. But however, the concept of transistor was there, solid state transistor was there a long time back in 1925, but it was not physically demonstrated. Okay. So there is a gentleman called Lilienfeld who actually demonstrated the who actually conceptualized the transistor in 1925. Okay. So this is just some trivial information which you should be aware of. So the point contact transistor, if you see that there was a semiconductor block, and what they have done, they have put two metal terminals on top of that, and they were measuring the current between these two terminals, and they were seeing that this I1 was able to control the I2. That means the magnitude of I2 was could be controlled by I1. So this was the first transistor action that was observed by this people in 1947. Okay, so now you see that the terminal nomenclature, base, emitter, and collector, how those come into picture. So as this substrate was used as the base of the entire stuff, so it was called your base terminal, and carriers were coming from this metal contact, so it was termed as emitter, and these carriers are moving via this path to this terminal, and that's why it was called collector. So if you see the today's convention of the BJT symbols, you you can easily see that the historical reasons behind the same thing. So this arrow is basically your emitter, this is your emitter, this is your base, and this is your collector, right? So you see that how this symbol came into being. So this was completely historical, and this was not due to the this BJT. This was owing to the first transistor demonstrated, that was a point contact junction transistor. Okay. So coming back to the second question, that in a BJT symbol, the arrowhead represents the direction of what? So we have two BJT symbols, right? This is one symbol, and this is another symbol. So this arrowhead is showing what basically? And how do you remember that what is the symbol of which kind? What is PNP and what is NPN?
So it's
If
showing
the arrow is outwards, we'll remember it as NPN, whereas if it is inwards, we'll remember as PNP. And the arrowhead represents the direction of current.
Okay, arrowhead represents the direction of current. Now, can you tell me why the left one is NPN? Means how that symbol came into being in the first place?
Yeah, because since in the first one, it is a NPN transistor. So P is the base and N is the emitter. So uh, the electrons goes from emitter to the base. So it will go from the N to P. But whereas the direction of current due to electrons, we will take the opposite sign of their flow.
Okay,
So
okay,
the direction
that
is
is
from
right.
base to emitter.
That is right. But there is another more interesting way to remember that. Okay, which you will never forget. Even in when we will discuss the MOSFET symbols, that part will also come into being. So tell me that this is a PN junction, right? So what is the flow of the current? The current flow is this way in a
Anode to
forward bias, right? In forward bias, this is the current flow direction. So whenever you see an arrow, the tip always suggests to the N side, and the opposite side is the P side. So similarly, here you can see that if you consider this arrow, so this you can consider it as a diode symbol, okay? Just without that dash. So this will be your P side, this will be your N side. Similarly, the other opposite thing is also valid for the other case. So this is your P side, this is your N side. And obviously you can guess the other terminal. This will be your P and this will be your N. Okay. So this is how you can remember. And why do we take this PN junction symbol? Because you remember that your emitter based junction is always generally forward biased in the general mode of operation, that is forward active. Okay. So this is one way to remember. And obviously in forward bias, as the direction of current will be in that direction of the arrow, so this arrow represents the direction of the current. Okay. So in a BJT symbol, the arrowhead represents the direction of the current. Then coming back to the third question, MOSFETs can be used as a switch in both analog and digital applications. Is the given statement true or false? What do you think? It is true. Why do you say? What is the difference between an analog switch and a digital switch, by the way? You can unmute and tell. So anyone? What is a switch and how do we connect a MOSFET switch? What is an analog switch? What is a digital switch? So in digital switch, it switches from 0 to 1 or 1 to 0, right? And what about analog switch? Okay, let's see. In analog switch, we can move to cutoff and active mode. Cutoff and active mode. No, not in terms of modes, just in terms of the transistor action, that in which terminal you will have the input and which is the controlling terminal, which is the controlled terminal. So by the way, what is a switch? Let us first discuss what is a switch. So this is basically a symbol of switch, right? In any case, if you have the tube light switch in your room also, that is also that can also be represented in this diagram, schematic diagram. So what is this called? This is called the pole, right? And this is called the throw. So, or in other terms, this is controlling and this is controlled. Okay. So we can have on and off two states depending upon what control you are giving at the pole. It can throw between this way or the cut off. So this, if this is on and off only, or in other words, if there is only one on state, we call it as a SPST switch or single pole single throw, right? Similarly, let's say we have, apart from off state, we have on to state. That's another state which we want to switch to. So then we have two on states, right? Then we call this kind of switches as SPDT or single pole double throw. Okay, MOSFETs acts as SP-ST switch. A single MOSFET acts as a SP-ST switch. Okay, how does this work? This is the gate terminal. This is, let's say, the drain terminal, and this is the source terminal. So by the way, how do you distinguish between the source and drain terminal? Because MOSFET is a symmetric device, right?
Based on the flow of electrons, like based on the applied voltage, like which terminal we are connecting to the which side. So based on that, the flow of carriers will be there. So based on that, we will determine which is source and which is drain.
So if I give you only this symbol and ask you to mention source and drain, so it does not matter if you just mention it source and it drain and vice versa. Okay, so because I have not mentioned the bias as of now, so now gate is your control terminal. How does gate control the flow of current in a MOSFET? Let's say you have a signal at this point. You want this signal to pass through the MOSFET. Okay, so this is basically, let's say it is an NMOS device. So this will be your N plus region and this is a P type region. So what you do, you apply a gate voltage, you keep it increasing. After some time, this VG crosses a voltage, we call it a threshold voltage. What happens at the threshold voltage? At the interface, this P type inverts to a N type. So creating a conductive bridge between the N type source and N type drain, and in between you will have a N type channel. Okay, so that is your on state. Then what happens? Whatever signal you have provided here can pass at the output. So this is your on state. And similarly, if your VG is less than this threshold voltage, in ideal scenario, this thing is not present. So you will have what kind of structure? You will have a P, you will have a N plus, then P, then N plus. So you will have a potential barriers across. So your carriers cannot easily move from one place to other. So that we called a off state. So this is how MOSFET is used as a switch. Now the question is, what is the difference between analog switch and digital switch? So let me just draw the output characteristics of a MOSFET. So this is in this plot. Are you familiar? Let's say VG is greater than VTH. Are you familiar with this plot? Okay. So now for analog switches, what is important is that if I have a very small signal means, let's say it can be your voice, it can be the signal which is being transmitted from your mobile antenna to the base station antenna. So there is a small signal around what? Around the bias point, at which place you have biased your drain and source. Let's say you have biased at this value. Let's say this is your quiescent point. Okay. Now what is happening? Now you are implying a or imposing a small signal. This small signal you are imposing on top of that. So what will happen? let's say this value is somewhat around 1.2 volt, and your this signal swing peak to peak was, let's say, 100 millivolt. Okay, that will be the range of your voice signals, and all it will be much lesser than that also. Okay, so what is the value across which that bias point will swing? So if this is your 1.2 volt, so 100 millivolt peak to peak means 50 millivolt plus this side, 50 millivolt that side. That means this will be your 1.25, this will be your 1.15. So between 1.15 volt and 1.25 volt, your this point will oscillate, right? This point will move this way and this way uh, along this curve. Okay, now let's see what will happen at the output side, means what we will get at through the current. So now if you just draw two perpendicular lines, what do you see? You see that your signal swing is reduced, right? So now from this concept, can you tell me, is this a good way to bias an analog switch? If not, then where should we bias the switch? It is very important concept, and you guys please unmute and let's have a discussion on this. This we are discussing analog switch, and we will eventually build that what is the key differences between analog switch and digital switch. So see, when we read a question, right, it is not important to get the answer. It is much more important to analyze each and every options you are having in the answers, why that is not true, and also what the question is actually asking. If you do not understand any single point, then you should go revisit the concepts. So it is not uh, sufficient to get to the correct answer only. We need to analyze the questions. Okay. So please tell me that if this bias point, let's say VQ1, is a good bias point for the analog switch to be in or not. Anyone? Just yes and no question.
No, sir.
It is not, right. So what do you suggest, that where should we bias that?
Is it active region?
Don't call me in, it is MOSFET, right? The active region is different. We classify the regions differently from that of a BJT. So you can tell me that in which part of this curve, this or you can just tell me what VDS value, high VDS value, low VDS value, where should I bias the switch?
Low VDS?
And
Because
why
in
do,
saturation doesn't matter whether you are increasing or decreasing.
right?
The
So
current would
if
be
I
similar.
bias it, so you mean to say we should bias it in this place, right?
Yes.
So if we bias it in this place, and then we have a signal swing of 50 millivolt, let's say we have a swing of this, so then my output is almost intact, right? So whatever the signal I intended to send, I will get I will get the signal at this terminal, right? So you see, in analog switches, the point of bias is very important. Okay, because why? We are dealing with very small signals compared to the bias voltage. So where do we bias the device? or for which application where we are biasing it, it is very important. For example, in case of amplifiers, you will like to bias it in this region, right? But that is not good for a switch, analog switch. For an analog switch, you want to bias at this region or very close to zero, VDS equal to zero, right? So remember this fact for the analog switches. This is very important. But in case of digital switches, where your values are 1 and 0, that means it is swinging from VDD to 0. So how does your digital signal look like? This is your analog signal, how this looks like. For a digital signal, it will be a pulses like this, okay? So what are the values? This value is VDD. Let's say for a certain technology, it is 1.8 volt. And this is your 0. So it does not matter, right, at which point you are biasing. As soon as your device is on or VGS is greater than VTH, the signal will pass or signal will pass, right? And as soon as your device is off or your VGS is less than VTH, signal will cut off, means it will not pass. So these are the considerations for analog switch and digital switches. There are other aspects, the frequency aspects, which we will try to avoid at this point in this course. Okay. When there will be frequency aspects, the capacitance will come into picture.
Sir, can you tell the biasing part and the analog part in brief again?
In the how the analog switch is biased.
Yes, sir.
Okay. So let's take two cases, right? This is case 1. This is case 2. What do you want from a switch? You want that when the device is on, when your gate is turned on, that means your VGS is greater than threshold voltage, then there will be a inversion layer. So your N plus drain, N plus source and your channel will get connected, right? That means your thing is on. Then what do you want? You want that your signal, whatever the signal, your voice, maybe a phone signal, whatever the signal you are putting into one terminal, let's say drain terminal, it should come out of the source terminal. In form of what does it come out? In form of current it comes out. Then you can put a load resistance and get it as a in terms of voltage. Okay. Now let's say you have biased your drain and source in this position. This is your VDS, remember. So what will happen? So this is your bias point. Let's say it is 1.2 volt. You have put 1.2 volt at your drain. On top of that, your small signal will swing. If this is your 1.2 volt, let's say this is your time axis and this is your VDS axis. So if you put a small signal, so it will swing on top of that. So this is what I have represented here. That your 1.2 volt will shift from 1.15 to 1.25 when we assume that the small signal has a peak to peak swing of 100 millivolt. Okay, it is nothing but your 1.2 plus 0.05 or 50 millivolt plus minus. Okay, so if you then see your output axis or your ID, this is only what is the current ID will flow, and you will just connect a resistor here, let's say 1 ohm, and you will then directly get this voltage out at this point, right? So your current should also swing or response in that way, right? In that scale. Otherwise, what will happen? You are getting a very small swing of the current. That is not desirable, right? So if you bias at this point, if you see that your this point and this point, how does it swing? It swings of a very low magnitude. This swing is very less. Now if you same thing, if you bias it at in the linear region, in a MOSFET, let's say this is called your linear region and this is called your saturation region. If you bias your switch at in linear region, so you can get the entire swing out of the output terminal, right? Means whatever you are putting here, you can get out here. So there is no damping effect there. Okay. So you want your switches to get biased in the linear region as close as to this value, zero value, for your analog switches. However, in case of your amplifiers, which we will see later, that you want this bias region is preferred. That is due to some different considerations. Okay. Is it clear now?
Yes, sir.
Okay. So these are the key aspects. So what do we take out from this? That MOSFET can be used as a switch in case of both analog and digital domains. But the difference is there in the way of biasing the switches. In one case, it is more stringent. The bias conditions are more stringent. That is analog switches. And in case of digital switches, it will just simply pass because your voltage swing is very high, right? These things we will discuss in much detail later. These are just warm-up questions. So moving on to the next question. The differential output of the difference amplifier is the amplification of what? Anyone?
Difference between the voltages of inputs.
Okay, in this context, tell me what is a difference amplifier you have come across? Do you remember this guy? Do anyone remember what is this?
Difference between the output of each transistor.
No, no, what is this? What is this device called? Do anyone remember? This is
Op-amp.
called op-amp,
Op amp.
right? So your op-amp is nothing but a difference amplifier, isn't it?
Can be used as a different amplifier.
Obviously, if you see the op-amp circuitry, if you see your op-amp will have multiple stages, right? If I draw the first stage for you, so there will be this PMOS connected, this is your diode connected MOSFET, this is your VDD, and there will be a current source. This is your V plus terminal, this is your V minus terminal. So this stuff here is called a difference amplifier, differential pair, which serves as the first stage of your op-amp. Okay. So your op-amp is basically in a zeroth order approximation, or let's say as a first order approximation, your op-amp is nothing but a difference amplifier. What does it do? It takes the difference between the non-inverting and inverting inputs and just multiply it with its internal gain, open loop gain, and then put out the V out. Okay. So the differential output of the difference amplifier is the amplification of difference between the voltage inputs. Okay. So moving on to the next question. This will be interesting. Okay. So which is the most preferred configuration for cascade amplifiers? Okay. This is cascade amplifiers. Achla Pardesi, you are telling that common emitter. Why do you say so? It is not sufficient to just give the right answer. We should also know what is the explanation.
Because in common emitter mode, we can give higher amount of currents.
Sorry, in common emitter amplifier?
Higher amount of output current can be is possible, right?
So what?
Higher amount of output current is possible, right?
So what?
So it is cascaded, so it will be easier to drive the next stage.
Why do you say so? By the way, okay, you guys are somewhat right, but let us try to look it in a different way. Different way means the approach is different. When you are given a question that uh, what is the most preferred configuration for something, we need to know that what is that something and what are the design constraints to do that something, right? In this case, that something is cascade configuration, right? Cascade amplifiers. So what is a cascade amplifier? First tell me this one. So whatever we are discussing here today, it is nothing to do with, or it is not only to do with these questions only. Okay, I am just trying to convey to you the approach of solving questions. Okay, so this approach will be followed in case of any future questions you tackle. So try to learn this approach, that how do you tackle the questions. So what is a cascade, by the way?
Sir, cascade amplifiers are the amplifiers
No, I
that
am
to
not asking about any kind of amplifiers. What is cascade? What do you mean by cascading?
सर कैस्केड मतलब कि वो दोनों जुड़े हैं ऐसा कलेक्टर से बीच में कलेक्टर होगा और वो एम्पलीफिकेशन बढ़ाने के लिए यूज करते हैं
Okay, so you mean to say that if this is A1, this is A2, I should get a, if I do not, if I just don't tell you anything, I just connect it in a black box and tell you that this gain is A, so this is your A1 times A2. Do you say that this is cascade?
यस सर
So everyone is convinced, right? This is cascade.
Yes, sir.
So now let's forget about this thing. Okay, so let's forget about amplifiers for a moment. So what are the key aspects for a cascade amplifier? There are three aspects. Can anyone tell me what are the aspects? Because why do we need cascade, right? One thing is that gain. So we should be concerned about the gain. These are the stages what we are talking about, that which stage we should use at these locations, right? Cascading is done to increase the gain, because one single stage, by the way, this is called your first stage, this is your second stage. Similarly, you can have multiple stages also. So one stage is not sufficient to give me the desired gain of a system. So I need to connect two stages in cascade configuration to get a higher gain. So gain is one very important aspect of a cascade configuration. What are the other two important aspects of cascade configurations?
Impedance.
What kind of impedance? You are right.
The, both the impedance, we should match the impedance, right, of
No,
the first stage and second stage.
impedance matching. No, impedance matching is there for maximum power transfer, right?
Yeah,
So let's say we are not concerned about power transfer. We are concerned about only voltage gain. Then power transfer does not matter. Impedance matching plays a very little role there.
and we should have infinite impedance, right?
Infinite
High input
impedance,
impedance.
where high input
High.
impedance, right, absolutely right. So your Rin should be higher, but that is not enough, right? Let's say my Rin is higher. You cannot have infinite, right? You have to have it with respect to something. Infinite is not there. It can have 1 mega ohm, 10 mega ohms, 100 mega ohms. That we consider as
Low output
infinite.
impedance.
Low output
Not low
impedance of
the out cap
the previous stage,
of
right?
transfer. Yeah,
So R out should be lower. Now Gain part, you understand that common emitter will give me the highest gain, right? Now, can anyone dwell deep into the fact that why R in and R out are important? Do you guys understand or do you want me to explain? Because there is a very critical concept hiding behind this.
Please
Prevent
explain.
loading.
Okay. Who told that? Loading, I heard something related to loading. I heard the word loading.
Yes, sir. To prevent loading.
Yeah, to prevent loading effect. Okay. Okay. Let's, for the sake of others, let me just explain what loading is basically. So these are very critical aspects. Okay. Not only for this course, for any analog or circuit or device courses, these are very key aspects. And for this, you do not need to know any previous information. Your circuit theory, even your basic Ohm's law, Kirchhoff's current law, and voltage law are sufficient. Loading effect. Let's say we have two things in cascade. Okay. Let's say simple resistive divider. So this is your V in, this is your V out. Okay. This is called load stage. Okay. Now let's say this is your R, this is your 2R, this is your R, and this is your 2R. So for the first time, let's say these two are different. So what is your, let's say this is Vx1, this is Vx2. What is your Vx1 in terms of V in? Anyone? This is simple resistive division. Anyone? What is Vx1 in terms of V input?
2/3 V1 V
2 by
input.
3 Vn.
And what is V out in terms of Vx2?
Same 2 by 3 Vx2.
2 by 3 Vx2. Now assume that if I connect it in the cascade mode, okay, what is my desired V out by V in? If I just simply go on and cascade these two, what do I expect? If I don't consider any constraint on the resistances, the gain of the two stages multiplied, right? 2 by 3 times 2 by 3. So this should give me 4 by 9. Do you see? This is one stage, this is the second stage. Is it okay with you that we expect 4 by 9?
Yes.
Now tell me the same circuit, when I connect it, what is the gain? Please calculate and tell me what is the gain. This is Vn, this is R, 2R, R, 2R. What is my V out by V in? So you need to first calculate this point, let's say Vx. Okay. Please tell me what is that? You have what? You have these two in series, 3R, this 3R and 2R in parallel. That means you will have what? You will have 3R parallel 2R,
4
right?
by 9.
4 by 9. Is it so? What is this Vx? What is 3R parallel to R? It is nothing but your 6/5, right? Is it okay?
Yes, sir.
So now what is Vx? So Vx is nothing but your 6/5 divided by 6/5 plus 1 times V in, and what is that? 6/11. Just correct me if I am doing the mathematics wrong. This is 6/5 R. This is R. So it will be 6/5 over 6/5 plus 1. So this will be 6/11 V in Vx. 6/11 V in. So what is your V out? V out will be your 6/11 V in times. This is again a resistive division. 2/3. This will be what? 2. So it will be 4/11, right? So you see your gain has reduced, right? You expected 4/9 when cascading 2 stages, right? But what you are getting 4/11. So this gain is reduced. So why do the gain get reduced? Until this, is everyone okay with this? Are you convinced that this is the values what we will get, what we expect,
Yes, sir.
and what is actual? So what is happening actually, if you look closely, that the gain of the first stage, that is your this Vx over V in. What was that earlier? Earlier that was 2/3, right? In this stage, it was 2/3. And now what do we get? We get 6/11. So 2/3 means your 6/9, right? So instead of 6/9, you are now getting 6/11. What do that? Why did that happen? This happens because your load stage is sucking out current out of the first stage, thus reducing the inherent gain of the first stage. So basically what is happening is that your load is responsible for reducing the gain of the first stage. So this is called your loading effect. Okay, this is not desired at all, because in a cascade configuration, suppose we want a gain of 20 and I have two stages. One stage has a gain of 10, another stage has a gain of 2. I will just connect it. I will not get a gain of 20. I will get a gain less than 20. So that is not desired. That will keep hindering in my design considerations. Okay. And you build up a circuit, connect it to something, and you'll see that the audio is not coming out. Okay. So what is the remedy of that? Let's say now we have two amplifier stages. Okay. This is A1, this is A2. And let's say this is my output resistance. I can show it in this way. This is my input resistance, R out 1, R out R in 2. That this input resistance is nothing but Thevenin resistance looking into this terminal. Okay. So what is the Vx here? So Vx, if This entire stuff I can replace it with R in 2. So this Vx will be your A1 times your total output resistance, right? Let's say if this is your current and this is your current, let's say this current is I. So this current will be your I times R out 1 in parallel with R in 2. What did you want? You wanted that I R times R out 1. Now you are getting this. So you have a R out 1 times R in 2 over R out 1 plus R in 2. How to get rid of this? Now if I say you that R in 2 is much greater than R out 1, that means you have a current flowing in this way, you have two resistances. This is your R out, this is your R in 2, this is your R out 1. So current will choose to go to the least resistive path. So if you can make this path almost infinity, that means your R in 2 is much greater than R out 1. So all the current will go through this path, right? So then your second stage is not sucking out any current. That means your inherent gain at this point is maintained. So your R in 2 has to be very higher than your R out 1. So this is the design consideration to get a good cascade connection or cascade amplifiers. Okay. So now what are the conditions? Let us revisit again. First thing is that your single stages should have sufficient gain. First condition. Second condition is that your R in should be higher because there will be other stages connected also, right? So R in general to let's say a nth stage has to be higher. R out has to be lower, right? So we will determine the stages in such a way that my input resistance is higher, output resistance is lower. Now, then once we have this knowledge, then we will study these three stages, that how does they behave with respect to each other. That we will do in the due course of time. But if you consider everything, gain, input resistance, output resistance, then your common emitter is a preferred choice of option. Okay, but again, having said that, your
அவங்க எல்லாம் க்ளீன் பண்றாங்க பாருங்க மேல அந்த
yeah, so having said that, your there are other configurations where you connect your common emitter as a first stage, or let's say the gain stage, followed by a common base or common collector to get good gain, overall gain, good input resistance, good output resistance. Okay, so this is the basic on which we use the multi-stage amplifier concept. Okay, so multi-stage amplifier concept came into picture from these things, that if I neglect or do not consider the frequency aspect of the amplifier as of now, then these three are the key aspect for any kind of amplifier application. So cascading is one way. In cascading, we see for these three options, and then we judge, we do a comparative study of common emitter, common base, and common collector, and then see which stage, which configuration is suited for what stage. I generally this is used as an input stage or the first stage, and followed by these two. But if I have to choose that only one kind of configuration I can use throughout, I will obviously choose the common emitter configuration. Okay. So did you get this concept of loading effect? This is very important actually. In MOSFETs, you will see that the input resistance of the MOSFETs are inherently infinite because there is a oxide present, that is an insulator present. So no DC current flows through that. Okay. But as soon as there are other aspects of multi-stage amplifiers also, Miller compensation and all, those things we will discuss in due course of time. Okay. But at this point, understand this much, that to prevent the loading effect, we use multi-stage, and the resistance choices are such that the output resistances should be lower and the input resistances should be higher for the next stage. Okay. So anyone have any question in this regard? Or anyone want me to explain it again? If not, then let's go for the BJT part. These were the warm-up questions. So I took some time to explain each and every concepts. I do not know how much you have grasped, but if you have any question, you can simply ask in the YouTube video link that will be posted, that to get this concept clear, or the discussion forum presented to you for the NPTEL course specifically. So I will explain that in next lecture also. Okay, if you have any questions. So moving forward, okay, let's go to the question number 1. So what is given that if we were to compare the energy diagram of 3 pieces of semiconducting materials, 2 n-type, this is n-type, this is n-type, and 1 p-type side by side, we will see something like that. Means, let's say I have a E0. What is E0 by the way?
Sir, we can't see it, sir.
Huh?
I can't see it, sir. Can you make it bigger?
Uh, no, this right
The
hand side diagram you are able to see.
yeah.
So what is E0?
Is it the ground state energy level?
No, we call it the vacuum level,
State
right?
vacuum.
So this is basically your, let's say this is your N type, this is P type, this is N type. Okay. You guys told me that you know band diagrams. Okay. Let's see. So for a P type, where should be my Fermi level? So these materials are not joined yet. These are
Near
individual
near
materials. Okay.
near valence band
For an
for
N
P
type,
type. P type valence band
for P type, let's say this is your EF. And for N type,
near conduction band.
near conduction band, let's say this is your EF. Now tell me one thing, that how was I able to draw this band diagram in this fashion? The question is that I have to, whenever I am drawing an energy band diagram, I have to take a reference energy level from which I draw the other bands. Okay, is that clear? So in case when these materials are disjointed, that means you have a separate p-type semiconductor block, separate n-type semiconductor block, separate p-type semiconductor block kept in isolation. Then I have taken the reference energy to be the vacuum energy level. Vacuum energy level is my then reference when nothing is connected. Okay. My question is that if why am I able to do so, and how did I able to draw these diagrams, means that why does this EC are at the same level,
Because they are in isolation, so there is no effect of others influencing it.
right? But just before that, what is this, by the way, this arrows, what does this energy refer to? The different
Energy
the
required to
difference
get out of
between the difference
the
between E0 and EC.
energy
Exactly.
Sorry, anyone?
energy required to get out of the crystal structure.
That is called what?
Excitation.
That is called your electron affinity, right? Electron affinity. Okay. Have you heard this term before, electron affinity? Okay. So electron affinity. Now tell me one thing. Electron affinity is a material property. That when I am talking about material property, I am referring the material to be silicon, the property inherent to the silicon. And if I take, it is a induced property which is dependent on doping. Okay. So can you guys tell me that if electron affinity is a material property or it varies depending upon the p and n type doping?
It's material property.
It is a material property, right? So if I take my E0 as a vacuum level, so when I have not connected the EC, the three materials, this EC are also will be at the same level. Is that okay?
Yes, sir.
Now, this is my EV. How did I draw the EV at the same level also? That means this gap I have taken also same for the three cases. And what is this? What is the difference? What is this called? The difference between conduction band and valence band?
EG.
This is your energy band gap. Now tell me if this is a material property or this is dependent on the doping.
Material property.
This is also a material property, right? So one thing is sure, under any circumstances, my E0, EC, and EV will follow each other. Is that okay? Because whatever happens due to doping or any other stuff, the differences will remain same because of the fact that these three materials are silicon. Is that okay?
Yes, sir.
Fine. Now tell me,
So
what does
E0 will also remain the same, or will E0 change?
E0 will come to later. I am telling that E0, EC, and EV will follow each other. I have not said that will it remain same or not. When the materials are not connected, then E0 is fixed. It is a reference. I can take any reference. I am taking E0 as a reference, okay? Because it is constant when the materials are not connected. The next statement I have made is that my EC and EV will always follow each other and E0, because the difference between E0 and EC is always constant. That is electron affinity. That is the silicon's property. Similarly, band gap is also silicon's property. Okay. Now tell me, what about EF? the Fermi level. What does it imply actually? By the way, this is your electronic energy, okay? What does your EF imply?
Free electrons.
No,
Probability of
no.
finding it.
Yeah, the probability of finding electrons. The probability is a, how would I put it? Is a statistical term. So it's an average sense, right? So EF is nothing but you can take it simply for understanding that it is the average energy of the electrons in a system. So now tell me, for an N-type material, will the average energy of the electrons be higher or lower?
Higher.
Higher than the intrinsic level if it was not doped, right? If the material is not doped, then the average energy is this. Now, if I dope the material with N-type, I have lots of electrons, then my average energy of the electron will go up. That means my EF will go up. So that's why my EF is closer to the conduction band. Do you follow? Anyone?
Can you please explain again why EF is higher for
Okay.
Android?
Uh, let's say if I have a intrinsic material, okay? What does intrinsic material mean? It means that I have equal number of holes and equal number of electrons, right? So my EI, what is EI? EI is nothing but your EF intrinsic. Means Fermi level or the average energy of the electron in an intrinsic material. Fine. Now let's say if I dope it with N-type, what I am essentially doing is that I am putting more electrons into the system. So this average energy will go up because this is nothing but electrons average energy. This is electronic energy. So do you agree if I have more electrons, the average will also go up?
Okay, get it.
Now, so this is my EF and this is my EF. And why does EF reduces for a p-type? Because my holes are more, right? So comparatively, my free electrons are lesser in comparison to the intrinsic state. What do I mean by that? 10 to the power 10 electrons, free electrons are there at T equal to 300 Kelvin, 10 to the power 10, 1.5 into 10 to the power 10 electrons per centimeter cube were there earlier. Now, if I dope it with, let's say, 10 to the power 16 acceptors doping. So, what will be my electron concentration? Electron concentration will go down to 10 to the power 4 because I know Np is equal to Ni square, law of mass action. So my average electrons, number of electrons are coming down in the system, free electrons are coming down in the system, right? So my average electronic energy in the system will also come down. That is why my EF will also come down. Is it okay?
Yes.
So now tell me, what is this difference called? What do we call this thing? This one we called electron affinity, this one we called band gap. What is this pink line is referring to? What is the word or what is the name for that? Anyone? This is called your work function. Have you heard of this term?
Yes, sir.
So now tell me one thing, that work function is a material property or it is a induced property?
It is induced property.
It is induced property, right? So keeping in mind these things, now let's move on to the band diagram when they will be joined. Now, when materials will get joined and we let the equilibrium to get achieved, what is the reference energy level? Will E0 remain my reference energy level?
Yes, and vacuum will be still the same level.
No, vacuum will not be the reference energy level, because now this is one system 1, this was system 2, this was system 3. Now I am joining this system to make a single system, okay? Single system in equilibrium, we have
Fermi level.
Fermi level same. Why? Because you have two regions. Let's say you have two regions. One region is electron rich and one region is electron deficient. So when you connect those things, so there will be diffusion taking place and many other aspects will be taking place, and all the things will come into a single balance. That means your average energy of the system will remain constant. That means your average energy of electrons throughout the entire system will remain constant. Okay, you see, here also it was constant, here also it was constant, here also it was constant, but these three were three different systems in equilibrium. Now when we join them, we have a single system. This is a single system. So the electronic energy in the single system will remain constant. So when the materials are joined, now my reference energy level or the constant energy level will be my Fermi level. Okay. Now what? Now interesting stuff will take place near the junctions. Let's say these are the two junctions that will be forming. First thing is what? Let's say away from the junction, what will happen? Away from the junction, this was my N type, this was my P type, this was my N type, right? Away from the junction, this will be my EC, this will be my EV. Similarly, this will be my EV, this will be my EC, EC, EV. How did I draw that? These are the same diagrams. This same diagram, this same distance, same distance. Fine. This will remain your EG. This will remain your EG because these are material property. This will never change even if you join the materials. And what about E naught? This will be my E naught or vacuum level. Why did I draw it like that? Anyone?
Difference between EV and E0.
EC and E0 or EV and E0 in that sense will remain same because this is silicon after all. Still it is silicon. Now at the junction what happens? Let us join these lines. I will not discuss the details on this because it will take me 2 hours to explain just this band diagram. Okay. Similar to PN junction, just assume that near the junction there will be a band bending. Okay. And similarly your E0 will also bend. Now can anyone tell me why will E0 bend? We never draw in band diagram the E0, but the significance of E0 is very important.
Because electron affinity is material property.
Exactly, because at this point also, this is what? This is your Q xi. Similarly, at this point also, this is what? This is your Eg. This point also it is Eg. This point it is also Q chi. Okay. So this is how you draw. This is how you draw a band diagram of any system. First, assume that the systems are individually isolated. Take vacuum level as the reference level. Then join them. Let them equilibrate. That means your Fermi level is now has become the reference level. You draw the Fermi reference level first and then draw the bands accordingly. So is it clear? Can you draw similar kind of band diagrams? This is just qualitative, okay? In quantitative measure, there will be many things in band diagrams. This is not for this course. In different course, we discuss those things. But qualitatively, can you draw band diagram of any PNP and PN junctions? This I will discuss again when we discuss about the MOSFETs in multiple subthreshold inversion, those kind of stuffs. Okay, depletion, how the band diagrams look like. So is it clear? Can you draw the band diagrams or do you have any questions still?
Sir, what is actually vacuum levels?
What is vacuum level? Very good question. Okay, let's say you have three slabs of semiconductors. Okay, let's say this is N, this is P, this is N. Fine. You have three materials. Now you want to see what is vacuum level. So did you remember the definition of potential from your 11th plus one standard? What is a potential?
You asking the formula or
No, no, the definition. Definition. Formula is something. Formula you can remember, right? The definition.
we can say the difference between the density of electrons.
No, 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 no. That is not the definition, right? Definition is that if you have a unit positive charge and if you want to bring another charge from infinity to this position, so what amount of work done you need to do? That is your potential definition, right?
Yeah.
So basically, vacuum level means the level at which the effect of this charge. So this charge will be basically throwing out fields, field lines. A unit positive charge will throw out field lines outwards. So that location where this field lines has no effect or the effect has been already died. So that location we called as a vacuum level. So ideally, what should be the distance, physical distance of vacuum level from any material?
Ideally, it should be infinity.
Ideally, it should be infinity, right? But when we talk about vacuum level in a energy band diagram, we talk about a something called local vacuum level. Okay. So what is local vacuum level? Local vacuum level is something just above this material, just outside this material. Because if you take any surface, let's say if you take a metal, this side is your metal. So if you have any charge here, no, this effect of field will die out 1 over x to the power 5 times proportional to. That means in a very small distance, you will have negligible effect of the field. So we can safely take this position as a local vacuum level. So for the band diagram, this is advanced stuff. So for the band diagram, you just assume that wherever your material is getting finished or the last surface, just above that you are taking the energy and how the energy looks like. That is your vacuum level, okay? Because you need to ultimately EC is what? EC is the conduction band, the highest energy level where your electrons can lie. Now, if you put more energy and kick that electron out, where will that electron go? It will just go outside as soon as it goes just outside the material, that we call it as the electron has reached this vacuum level. Okay. So when we talk about vacuum level in a semiconductor band diagram parlance, we talk about local vacuum levels. Okay. This is the energy of electron just outside the material. Is that okay? Okay. So yeah, good point. I just remembered one point. Go back and check the definition of these things. Okay. Electron affinity, electron affinity, ionization potential, work function, normal potential, electric field. Okay, just go and check your any of the 11th or 12th standard textbook, NCRT book or anything like that, whichever board you have graduated from. Just go and revisit the basic definitions of these terms. Okay, then try to correlate with what we have discussed today. Okay, that basic definitions you should always remember, because formulas you may forget. You can get to that formula by from those definitions also. Okay, so this is how you draw a band diagram. So in the comment section of the YouTube video where there will be posted, I will refer to one of my earlier with the similar kind of NPTEL course recordings. There the band diagram has been discussed in much detail. Okay, if you are interested, you can revisit that. So moving on to the second question. Bipolar junction transistor function is usually considered in terms of currents. A relatively small current through one of the transistor's terminal exerts control over a much larger current. Draw the directions of all currents in these two transistors and mention what is the control and what is the controlled. So can you tell me what are the currents in a BJT? Just let me draw a BJT first. Okay, let me draw it in scale. So this is your emitter, this is your base, emitter, base, this is your collector. Okay, so you will have a depletion region. Similarly, you will have a depletion region here. So let's say this is N++, this is P, This is N minus, for example. This is forward biased and this is reverse biased. So can you tell me what are the current components in this? Means how the currents flow. First thing is that this junction we call it as EBJ or emitter based junction, okay? And this junction we call it as CBJ, collector based junction. So what happens is that let's say your electrons are injected in this. Electrons are injected, then electron will come here in the base region and electron will become what? Electron will become minority carriers in p-type base. Then electron will start to diffuse, minority carrier diffuses, right? And then because of your base region being very narrow, some of the minority carrier leak through and this reach the collector terminal, okay? And what happens in the meantime? Holes are injected in this path and this some of the minority carriers gets recombined here, and again being a PN junction some holes will be injected in this way also, and some it will get recombined through some other process in this place. So this constitute one current. Because this is the flow of electron, current will be in different direction. This is your IE. So this is your flow of holes. So current will be in this direction, IB, and current will be, this is the flow of electron, current flow will be in this direction, IC. So given that you have read the lectures, can you tell me what is the controlling current and what is the controlled current?
IB is the controlling current, IC is the controlling.
IB is the controlling current. Why do you say so? By the way, tell me one thing. Do actually IB controls the current or something else controls the current?
VB is.
This voltage actually controls the current, right?
Yeah.
So you can take it in a sense that IB is controlling your current and this is the controlled current. Okay. So in a NPN transistor, the symbols and notation we have already discussed. So what is this? First thing, PN junction, point out the PN junction. This is P, this is N, this is N. Then second thing is, this is emitter, this is base, this is collector. What are the direction of the current? Current is flowing in this direction. This is the current coming out of emitter. This is the current IB. This is current IE. This is current IC. See, this is IC coming in, base current coming in, emitter current coming out. So this is your controlling, this is your controlled. Okay. Similarly, for an PNP transistor, so this is your P type arrow. First thing is you see the arrow and figure out what is the PN junction there. Then this is P. So this will be your emitter. This will be your base. This will be your collector. So current is coming in emitter. This will be going out. This will be going out, IB. Okay. So this will be your again controlling. This will be controlled. So I want to ask you one question regarding this. So what do you think a BJT is? A CCCS or a VCCS? Current controlled?
VCCS.
No, you just think it through. Current source.
Yes.
Right now, what we have discussed, your IV is controlling, right? And your IC is controlled. That means it is a current control current source. But again, I have also told you that VB is actually controlling the current. So is it a voltage control current source?
I think in the lectures it's mentioned as CCCS.
No. Don't tell me that it is mentioned in the lectures. I want to know what do you think? It is not for
I
today.
think it's VCCS.
I'll ask you it in the beginning of the next lecture. Okay, you have 1 week time. You think it yourself, convince, and even if both are true, some one is true, other is true. It does not matter whatever the answer is. I am not interested if you give me the right answer or the wrong answer. If your wrong answer has a logic itself, I will accept that also. Okay. Your wrong answers should also have a logic that why you have thought that answer to be. Okay. So it is not about getting the right answer correct or the answer correct. Your wrong answer has to be having some justification. In my university, there is a professor in microwave circuits who used to call me after the exams, and he used to ask me that these questions you have made it wrong. These 5 questions you have made it wrong. So I have deducted 5 marks. Now tell me that why have you thought of these answers? If you can explain me that why have you made these wrong assumptions, then I'll give you marks. So you see the philosophy behind that. So they made you to think that if you are just not guessing the answers, right? You should have a proper logical explanation of that. Okay.
Sir,
So yeah,
sir, IV only control the recombination rate. By controlling recombination,
it is the
anyone
other way
control the.
around. It is the other way around. The due to the recombination only IB flows, not IB controls the recombination. The recombination in the base region is only contributing to your IB. What does recombination gets controlled by? Recombination gets controlled by many things. The doping in the base region, the doping of the emitter with respect to base, right? The width of the base. See your, if you see the minority carrier profile in the base, right, it is just decaying like this. If you have a longer base, okay, let's say this is your EBJ, this is your CBJ. I am ignoring the depletion region in between. Okay, now let's say this is your W1. Fine. So your things are decaying like e to the power minus x kind of fashion. Okay. Now what? Now if you just reduce this W1, let's say I terminate my CBJ at this point, then this part will be almost linear, right? Why will it be linear? It will be linear because the Taylor series approximation of your e to the power minus x. What is e to the power minus x? 1 minus x plus x square by factorial 2 minus x cube by factorial 3 plus this. So these higher terms if you ignore, then it is just 1 minus x, right?
Yes, sir.
You see why it is that exponential recombination has become linear in your BJT. This is the reason. So it is other way around, not that the IB controls a recombination. Due to the recombination, your IB flows. Okay,
Okay.
just think on this. Is a very good tongue twister. Okay, next question is that this will be the last question due to the time. So A technician uses a multimeter's diode check function. So have you guys anyone used the multimeters or DMM, digital multimeters, that orange color stuff?
Yes, sir.
So in multimeter you have seen one diode check option, right?
Yeah.
To check the connectivity.
Yeah, to check the connectivity and to check that whether my PN junction is working or not. Right. So let's say if I have a PN junction, if you see the PN junction, there is a silver color bar here, right? So this determines your P terminal, this determines your N terminal. So if you connect that, let's say if you connected your N terminal with black probe and this is your red probe and this is you connect to your DMM, digital multimeter, so you will get a voltage reading of forward bias in case of 0.5 to 0.7 volt, and if it is reverse biased, if you connect it in opposite way, so your voltage will be kind of 1 volt, right? So have you seen this diode check option?
Yeah, I know the digital reverse correction.
Okay, now tell me, why does this get shown that way? If you see the internal circuitry, let's say this is a battery, then they have a eye test. Okay, inside that this is inside the DMM. Okay, inside the DMM. So you have a eye test, and then you have a voltmeter connected to that. This is a voltmeter, and then you have a this is your DUT. What is DUT, by the way?
Device under test.
Yeah, DUT is your device under test. Means you connect your device in this way, device under test. Fine. Now let's say you connect your diode in this way, right? Let me just copy this, copy. Okay, just think that you have connected your diode in this fashion, that it is like this. Okay, so what happens? So this is a voltmeter, right? This is, let's say, VD, and let's say this is your ID. So what is your diode characteristics? Diode characteristics is something like this, right? Do you agree, guys?
Yeah.
Now let's say this is, by the way, the battery, the pencil battery you put into the DMM, right? So now let's say you have a eye test of, let's say, zero point 0.1 milliampere. Okay, your voltmeter has a very large series resistance, right? That means there will be no current flowing, through this path. So entire current will flow through your diode, right? Let's say if that is the case, then this is the 0.1 milliampere. So what is the voltage corresponding to that? This will be somewhere very close to your threshold voltage, right? Or the knee, or you call it cut-in voltage, right? So in a series path, if you have a current source connected and any DUT connected, the entire current will flow through this. So what is the voltage developed across this? That will be determined by the diode characteristics or the DUT characteristics. In case of, if diode is in forward bias and I am injecting a 0.1 milliampere current, so that will lead to the voltage at which the diode has that cut-in voltage, or this voltage corresponding to this current level in that IV characteristics. That's why your voltmeter then reads around 0.5 to 0.7 volt depending upon what level of current you are pushing in. Are you at this point, or at this point? Okay. So this is to check whether your diode is in forward bias or not. So whenever you see in your digital multimeter a voltage range around this value, so you can assume that this is a PN junction and that diode is connected in a forward bias configuration. Okay. Now tell me, in reverse bias case, why it is showing always 1 volt. In the same ideology can, or the same explanation guidelines what I have just mentioned, can anyone tell me if the diode is connected, let's say if the diode is connected this way, then what happens? Anyone?
Current will flow through the other path, right?
Current will flow through this path?
No, the other
Obviously,
path.
no, it has to flow, right? This resistance is very high. You can consider voltmeter resistance as open circuit. So current will flow through diode. Okay, that is for sure, because this current source principle otherwise will get violated. So now think that in reverse bias, a huge amount of current is flowing in the other direction. What is the significance? From this plot, IDVD, can you tell me?
It's breakdown.
Exactly. So your current is now at this point, right? This is your minus 0.1 milliampere. So you will always see this voltage, this VBR. This VBR is around your 1 volt. So any current value above this microampere, or this is very little, it is around nanoampere range. Above this nanoampere, this I test will obviously be much higher than that nanoampere. So it will put the diode into reverse breakdown and it will always show this VBR. Okay. So it is all about how you read the diode characteristics. If you have a current source in a series path, that current has to flow through that path. If that current flows through that path, that means you figure out that point in the IV characteristics and read out the corresponding voltage value. Is that okay?
सर
Yeah.
सर तो फिर डायोड को हम स्विच की तरह यूज नहीं कर सकते हैं
No,
मतलब
no,
हम तो
this is not for using switch. This is to check. This is in DMM to check what is the status of the
सर
diode. Diode,
सर
we can use it as a switch, right?
बट करंट इज फ्लोइंग
But
ब्रेकडाउन
exactly, but in switch, do you put current source, high value of current source? If you are willing to put high value of current source in the switch, then obviously you cannot use diode as a switch.
ओके
Do you see what I am telling?
यस सर
It is all depending upon whether you are using a voltage source or a current source. Generally, in the switch applications where diodes are employed, the voltage source you are connecting through the diode, not the forceful current source. This is a forceful current source, right?
यस सर
Current has to flow in that series branch. So given that in the question it is mentioned that you have a device with 3 terminals, 1, 2 and 3. So when you connect your, this is 2 and 3 are connected. When you connect your 2 and 3 terminal, you see a voltage of this in your diode check option. That means what? First thing we can clarify that this is your N type and this is your P type. Is that okay? That it is a PN junction in forward bias connection.
Yes, sir.
Similarly, in this case also, it is a, so this is your P type and this is N type.
Yes.
So now what do you have? You have a DUT who has three terminals. This is P type, this is P type, this is N type. So this is 1, this is 2 and this is 3. So what was the V23 you were reading? V23 value you were reading as 0.605 volt and V13 you were reading as 0.617 volt. So first thing is that it is a PNP transistor, okay? And if it is a PNP transistor, this N terminal is your base. Now you need to distinguish between 1 and 2, whether 1 is emitter or 2 is emitter, whether 1 is collector or 2 is collector. How do you do that? Any idea? Read these voltages carefully. You see that one voltage is higher than other.
Yes, sir.
So
So
what
the
is
lower voltage is collector
lower voltage is collector? Absolutely right. But now you have to tell me why. This is a
because
guess,
it's
right?
lightly doped,
And so, yeah, you are
much
right.
lightly
Absolutely
doped.
right. So,
So the resistance,
no. Just think you are on the right track. Collector is lightly doped, right? That means your N2 is much less than N1. Sorry, P2, the P type, right? So P2 is less than P1. So what? So what about this voltage? How does this voltage relate to your doping? Come on, I know you know this thing. Just you are not thinking. So by the way, what is this cut-in voltage? This cut-in voltage will give you a value very close to your built-in voltage in the diode. What is the built-in voltage in the diode? Phi t natural log of N anode times Na means your acceptor, N donor by Ni square. Do you recognize this formula? This reading is nothing but your close to your built-in voltage, right?
okay, got it.
So in one case, V23, what will you have? You have phi t ln N2 N3 divided by Ni square. In another case, you have V13, that is phi t ln N1 N2 N3 by Ni square. You see that if your N1, messing with that terminology. So if your P1 is greater than P2, that means your V13 will be greater than V23 because log scale will obviously tune it down a little bit. Do you get it? Others? Anyone?
Yes, sir.
Do you get it right?
Yes, sir. Sir. I got it.
So it is the doping of the emitter is much more than the doping of collector. your emitter will be, your P1 will be around 10 to the power 20 per centimeter cube, while your this P2 or the collector will be as a doping of 10 to the power 16 to 17 per centimeter cube. So I can safely say that P1 is my emitter, this is my collector, this is my base upon this test, right? So please do the, whoever have the access of your electronic circuit lab, go to your lab and use that DMM to take a PJT. Just convince yourself that this is the case. Okay. So we will stop here today. So if you have any questions, you can ask now.
Sir, what is the reason we collector is less doped than emitter?
Next day I'll talk. It is a very lengthy topic. Collector is, see, emitter is highly doped. Everything is with respect to base. Okay, emitter is highly doped with respect to base because we want to. Let me just tell you
No,
in
sir,
this way.
base, I know the story of base. I
No, no,
want to
it
know
is
that.
it is with respect to base. Emitter is highly doped with respect to base, and modern day transistors, base is highly doped with respect to collector. Base is highly doped with respect to collector due to avoidance of the, due to, or the diminishing of the base width modulation that we will discuss in the next class. Okay, why
The
base width
base
modul?
is the base is least dope.
No, no,
Or
that base is least dope. That was in the earlier convention. Earlier transistor used to be like that, but in current transistors, if I draw you the profile, if I draw you the, let's say this is your PNP transistor, this is P, this is N, this is P. So this will be something like this. You see, collector is basically divided into two regions. The closer to this will be least doped. So this is your 10 to the power 20. This is your 10 to the power 18. Let's say this is your 10 to the power 16, and then collector again doped to 10 to the power 20. So this P will be closer to the base region. It will be lightly doped because to reduce the base width modulation. Because due to the reverse bias, this depletion region, you want most of the depletion to take into the collector region. Okay.
yes, sir.
So this is how it is in the modern day transistors. But in the earlier transistor, you are right that base used to have a lesser doping than collector. But nowadays, as the device dimension are getting shrinked, and to get the base width modulation much lesser, we use this kind of engineering, and also we sometimes use silicon germanium base. This is silicon, this is silicon. These are called heterojunction bipolar transistor. If time permits, I will discuss, I will touch upon this in later lectures. Otherwise, as of now, you take it in this way.
Yes, sir.
Okay. Okay, so thank you everyone. Let's close the session here.
Thank you.